Hello everyone. Can anyone confirm? Am I audible?
Yes, sir.
And my screen is visible?
Yes, sir.
Okay. So let's start. Good evening everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL TA for the course Introduction to Probability Theory and Statistics. This course is offered by Professor S. Dharmaraj. He is a professor in IIT Delhi. Okay. So this is the 8 week of the 12-week course. So if anyone have any doubt, they can ask me. Okay. Okay. So in the previous 7 weeks, we have discussed about a lot of concepts related to probability theory. Okay. And this is the last class or last week or last lecture for the probability theory. And in week 9 and onwards, we will discuss about the statistics actually. Okay. So up to this week, we have discussed about like basics of probability. And in which we have discussed about random experiments, sample space, events, axioms of probabilities, conditional probability, independence of events, and Bayes theorem, etc. In week second, we have discussed about random variables. In which we have discussed about the definition of random variables, what is cumulative distribution function, the type of random variables, how to formulate probability mass function and probability density function, and the distribution of functions of random variables. In week 3, we have discussed about like moments and inequalities. In moments and inequalities, we have like evaluated mean and variance of the different distributions, higher order moments, moment inequalities like Jensen inequality, Chebyshev's inequality, Markov inequality, etc. And then we have discussed about generating functions like margin, like moment generating function, probability generating function, and characteristics functions. Okay, in week 4, we have discussed about some standard distribution. Standard, discrete, and continuous distribution. Okay, like we have discussed about different kinds of discrete distributions like binomial, Bernoulli, Poisson, geometric, negative binomial, etc. And for the continuous type of distributions, we have discussed about normal, exponential, gamma, beta, and etc. Okay, so and we have also discussed about the properties that is mean, variance, skewness, and all the other statistical characteristics of these distributions. Okay, now in week four we have discussed these things. In week 5 we have discussed about like higher dimensional distribution. Higher dimensional distribution in which we have discussed about bivariate and multivariate distributions, their joint probability density function and joint probability mass function, the independent of those random variables. Also, how to calculate the marginal distribution with the help of those joint probability distribution or probability mass functions. Okay. In week 6, we have discussed about functions of several random variables. Functions of several random variables. Okay, that is in this particular topic, we have discussed about the transformations of random variable, order statistics, conditional distribution, and the random sum. Okay, in the last week, that is in the 7th week, we have discussed about the cross moments. Cross moments in which we have discussed about the moments of functions of several random variables, the variance covariance matrix, the correlation coefficients, the concept of correlation and regression, and the conditional expectation, and at last conditional variance, and how to calculate the conditional variance or conditional expectation when we are given the joint density or joint distribution. Okay. So these are the topics we have covered so far up to the last 7 weeks. Okay. So now we are at the 8th week of a 12-week course. And in this week, we will discuss about the limiting distributions. Okay. So in this week, we will discuss about limiting distributions, in which we have mainly 3 topics that we are going to cover. The first one is mode of convergence. And the second is law of large numbers. And the third is central limit theorem. These are the topics we will discuss today. And by completing these topics, we have completed the probability theory part for this course. Okay. So anyone have any kind of doubts, then he or she may ask. Okay. So let's start from the first topic, that is modes of convergence. Okay, these are the topic sir has already discussed in a very comprehensive format, but I'm just taking a snapshot of those topics, and after that we will solve some numericals based on these topics. Okay, so actually there are 4 modes of convergence in probability. Okay, so there are 4 modes of convergence. The first one is convergence in distribution. Is my screen visible now?
Yes, sir.
Okay, is my screen
Yes, sir.
visible? Okay, thank you.
Yes, sir.
Convergence in distribution. The second one is convergence in probability. The third one is like convergence moment, or we can say the convergence in Rth moment. And the last one, convergence is almost surely. That is also abbreviated as AS. Okay. The convergence in distribution as D, convergence in probability as P. This one is R or L to the power R. Okay. So use as your convenience. Okay. Also, there are some hierarchy of their strongness or weakness. So these are as we go from 1 to 2, 2 to 3, 3 to 4, these are we can kind of say that it is stronger. That is like convergence in probability is like weak in nature as compared to convergence is almost surely. So these are the strongest one actually. Okay. There's not any hard and fast rule, but it is the kind of nature we can see. Okay. So let's discuss about one by one. So first discuss about convergence in distribution. The first one is convergence in distribution. Okay. So okay. So in this topic, let me write the definition. Suppose we have a sequence of random variables. Actually, We don't have like, suppose we have x1, which follows some distribution with some parameters, x2, which follows some other distribution maybe, or the same distribution with different value of parameters, and x3, x4, and so on. So we have a sequence of random variables. Okay. So there we need to find a random variable which follows some particular distribution. Okay. And all those sequences converges to that distribution. Okay. So these are the concept of modes of convergence or convergence. Like let x1, x2 up to xn up to, these are like be a sequence of random variables with cumulative distribution function CDF of f1, f2, fn, and so on respectively. Okay. Then we say that sorry, xn, the sequence of random variable xn, where n is taken from the values 1 to up to infinity. Then we say that the sequence of random variable xn converges in distribution to random variable x, as denoted by like xn converges to x in distribution D if limit n tends to infinity, fn of x equal to fx for all x, where f is the cumulative distribution function or CDF of the random variable x. Okay, so this is the definition. Okay, how can we say that? When we have a sequence of random variables and with their corresponding CDF, then if xn, the sequence of random variable, converges in distribution, which is denoted as this xn converges to x in distribution, if this condition satisfied. The condition is if limit n tends to infinity, fn x equals fx. Okay, so let's like understand this topic with the help of an example. These are already discussed in the lecture. Okay, let me take the same example. So like let we have a probability space, okay, omega fp, it is a probability space. Okay, let the sequence of random variable xn where n equal to 1, 2, and so on, okay, be a sequence of random variables defined on the same probability space omega fn p, as like we have defined the random variable xn such a way omega to the real number r such that xn of omega, or we can say that w, okay, omega or w equal to 1 by n for n equals 1, 2, and so on. Okay. Now, this is a question. Okay, we need to check the convergence of this random variable. Okay, the sequence of random variable actually. Okay, so now our aim is to find out the CDF of the sequence of random variable. Okay, the first, so we can say that now we will find out the CDF of sequence of random variables. Okay, so as we can see, we can define fxn equal to either 0 or 1 when x is less than 1 by n, x is greater than or equal to 1 by n. Okay, because here xn defined as 1 by n. So with the help of those, we can define the CDF of fnx equal to 0 when the value of x less than 1 by n, and 1 when the value of x is either greater than or equal to 1 by n for n equals 1, 2, and so on. Okay, now we need to find the limiting case. Now we need to find the limiting case. So now let's find limit of n tends to infinity fnx, which is, since it is 0 or 1, 0 and 0. Okay, so when we like take the limit n tends to infinity, then 1 by n comes out to be 0 and 1 by n comes out to be 0, so that the same distribution is converted into fnx, which is equal to 0 when x is less than 0 and 1 when x is greater than or equal to 0. Okay, now let's define fx. Now let's define fx like in a similar manner when x is greater than, sorry, less than 0, x is greater than or equal to 0. Since we can see it is a proper CDF, how can we say that? Here the fx satisfies all the property of a CDF. Minimum value contains 0, maximum is 1, constant, monotonic in nature. All the property that we have discussed during the given during that lecture, in which a given function is a valid CDF or not. This fx follows the same. So we say that fx is the CDF. Fx is a proper CDF of random variable x. Say random variable x. Since limit n tends to infinity, fnx is equal to fx. That means we have a random variable x for the sequence of random variable xn. We have found the random variable x for a sequence of random variable xn, and the corresponding fx for the CDF of the sequence of random variable fnx. Okay, so this implies xn converges to x in distribution. This is what we are going to like evaluate or find out. So we have find out the xn is converges to x in distribution. Okay, I hope it is clear. Is there any doubt? Okay, if you have any doubt, then please ask. Okay, now we will discuss about the convergence in probability, the second convergence. Is there anyone? No? Am I audible? No? Like,
Yes, sir.
okay, and my screen is also visible.
Yes, sir.
Okay, so we have discussed the convergence in distribution. Now the second modes of convergence in probability. Let's define again. So again, let we have x1, x2, xn be a sequence of random variables defined on the probability space. Suppose omega, f and p. Okay, so we say that the sequence of random variable xn or n equals 1, 2, and so on converges in probability to X. That is, we can also write the same statement that Xn, the sequence of random variable Xn, converges to X in probability if for any epsilon greater than 0, limit n tends to infinity, the probability that Xn minus X is greater than epsilon equals 0. Okay, if this condition satisfied, then we say that the random variable X, sorry, the sequence of random variable Xn converges to the random variable X in probability. Okay, again, if we can solve this with the help of an example. Like let Xn be a random sequence, be a sequence of random variables defined on omega f and p such that probability that Xn equals 0 equals 1 upon 1 minus 1 by n, and probability that Xn equals 1, not 1, n equals 1 by n for n equals 1, 2, and so on. Okay, this is the example. Okay, so now we can take any epsilon. Okay, so let for any epsilon greater than this, okay, greater than 0, that is positive epsilon, probability that the absolute of Xn is greater than epsilon equal to 1 by n if epsilon is like less than n, and 0 if epsilon is greater than or equal to n. Okay, now we'll go to check the limiting condition. Okay, for the convergence in probability. Now the limit n tends to infinity, probability that absolute of Xn is greater than epsilon equal to 0, or we can directly say that limit n tends to infinity, probability that Xn minus 0 greater than epsilon equal to 0. Okay, so if this expression or this term star, you can see, compare this with the help of this equation, the equation in the definition, the last line. You can find out the Xn, the value of X is here 0. Okay, so that means this implies the sequence of random variable Xn converges to 0 in probability. Okay, so it may also possible. So let's write a note here. Sometimes the sequence of random variables, like sometimes the sequence of random variables converges to a constant. Like here, we will see that it converges to 0. Okay, so sometimes it may possible the sequence of random variable converges to a fixed point, a scalar, a constant, okay, in probability. So this is how the convergence in probability it's defined. Now the next one is convergence in rth moment. Okay, so the definition will be like this. Let r is greater than 0, x1, x2, x1 be a sequence of random variables defined on this the probability space omega f and p such that expected value of absolute x and r is less than infinity. That means the expected rth expectation of xn is finite or exist for n equal to 1, 2, and so on. Then, like we say that xn, the sequence of random variable, converges to x in rth moment if expected value of absolute x r is finite and limit n tends to infinity, expected value of absolute difference of xn minus x, sorry, xn minus x power r equals 0. Okay, if this condition satisfy, then we say that the sequence of random variables converges to sequence of random variable converges to like at x in rth moment. Okay, so this can be like here xn converges to x in rth moment. Okay, let's again solve one example related to this. Like let x1, x2, xn be a sequence of random variables with expectation of xi equal to mu for I equal to 1, 2 and variance of xi equal to sigma square for I equal to 1, 2 so on exist. Okay, so at least the second order moment exists. Okay, also now the new now we will define the new random variable actually. Now like the new random variable is defined. Okay, and that random variable is like that random variable is like x bar. Okay, which is nothing but the summation of x1 plus x2 plus xn divided by n. Okay, or the summation of xi are also written as sn and divided by n. Okay. So now let's take the expectation of this new random variable. Okay. So, okay. Expectation of Sn by n minus of mu square, which is also like written as expected value of Sn minus n times mu whole square upon n square. Okay. So here it is given like if we have defined like x1, x2, xn be a sequence of random variable. Okay, and these are like identically distributed actually. Expectation of xi equal to mu. Okay, it is given expectation of xi equal to mu for all value of I. Okay, okay, let me write it. Okay, so that means expectation of Sn, if you can see, since expectation of Sn is expected value of x1 plus x2 plus xn. So this implies n times of mu. Okay. Also, uh, expected value of x minus expectation of x whole square is defined as nothing but variance of x. Okay. These are the cases. Okay. So this that means this value like expected value of Sn minus n mu whole square upon n square is nothing but 1 upon n square is taken as common. Sn minus n mu whole square is nothing but variance of Sn. Okay. So we like find that this case. Now also since x1, x2 and xn are have the same variance sigma square as well, and xi are like sequence of independent random variable. So that means we can also write this n square into n times of sigma square. Okay, and at last n is cancel out. So after like solving, we will get Sn minus n minus mu whole square is nothing but sigma square by n. Okay, so this is the case. Now taking the limit. Now limit n tends to infinity. Expected value of Sn by n minus mu whole square is nothing but 0 because n is in denominator. And so from the above, we conclude that what? So we conclude Sn divided by n converges to mu in R. Here the value of R equal to 2 actually. If you can like see, the value of R is nothing but 2. Or we can say that xn converges to x in R equal to 2. Sorry, not x actually, it's mu. No? Okay, the sequence of random variable xn converges to mu at R equal to 2, that is at the second moment. So this is how the convergence in moments, rth moment takes place. Now the next topic is the last one, convergence is almost surely. Convergence in almost surely, or AS can usually write it like this. So again, let's define, let x1, x2, xn be a sequence of random variables defined on the probability space omega f and p. Then we say that the sequence of random variable xn for n equal to 1, 2, and so on converges in almost surely to x if the probability of limit n tends to infinity xn equal to x is nothing but 1. That is, like we can write x1 converges to x almost surely if like like this. Okay, that is we can say that xn converges to x. Okay, so this is how we define the convergence is almost surely. We need to check the probability that limit n tends to infinity xn equal to x equals 1. So this probability must be equal to 1. Okay, so again, let's have an example for the same so that we can have one result as well. Okay, so let omega f and p be a probability space. Also, let xn for n equal to 1, 2, and so on be a sequence of random variables defined on the probability space omega f p as xn such that omega to r x omega omega or w, okay, small omega or w, x omega equal to 1 plus 1 by n for n equals 1, 2, and so on. Okay. So this is the question. Now, for all omega belongs to capital Omega, limit n tends to infinity, x and omega equal to 1. Okay. So this implies like probability that omega belongs to capital Omega in such that xn equals omega, and this will converges to the probability 1, which is also like probability that the whole sample space, which is equal to 1, as we have already know. So we say that xn converges to 1 almost surely. Okay. So this is how we check the convergence. Okay. And now the same, even the same example is used for other convergence and you will find the same results. Now we have a remark actually. Okay. Since we have discussed all the 4 modes of convergence, we have a remark. Okay. A remark will be like, suppose here like xn converges to x in probability. Okay. So this implies xn converges to x in distribution as well. Okay. If xn converges to x in probability, so this implies xn converges to x in distribution, but xn converges to x in distribution does not imply xn converges to x in probability. So that means distribution is quite the lower one or the weakest one in the modes of convergence, and just above the convergence in probability. Okay. And then the rest of the two will be like this, like xn converges to x almost surely. Okay. This will imply like this. Okay. If xn converges to x almost surely, then that means it implies xn converges to x in probability, which further implies xn converges to x in distribution. Okay. And in the other direction as well, like xn converges to x in r in moment r equal to 1. Okay. So this also converges to in probability. Also, actually, for the higher value of r, it becomes more stronger. Oh, sorry, it becomes stronger. Okay. So that means, like, if I can write here like this, if xn converges to x in r equal to some number n, which is quite larger, for example, or r equal to r, even we can say. Okay, so this can be like converges to this. The more the value or the higher the value of r, the stronger the modes of convergence. Okay, so this is how like the different modes of convergence are like connected to each other. Okay, so is there any doubt up to this point?
No, sir.
Okay. Okay, then. So up to this point, we have completed the modes of convergence. Now the second topic is law of large number. So there are mainly two law of large number. The first one is weak law of large number, and the second one is strong law of large number. Okay. So weak law of large numbers. In short, we will abbreviate it as WLLN. The theorem is like let x1, x2, xn be a sequence of random variables with mean mu and finite variance sigma square. Okay, so it must at least second order or at least finite variance is there, second order moment exist. Then for any epsilon greater than 0, we have like probability that x1 plus x2 plus xn divided by n, sorry, divided by n minus of mu is greater than epsilon. This value is less than or equal to sigma square divided by n epsilon square. Okay. Also, limit n tends to infinity, the probability that x1 plus x2 plus xn divided by n minus mu is greater than epsilon is 0. If we take the limit n tends to infinity, the same quantity comes out to be 0. Okay, so this is the weak law of large number. So that means like we call it actually weak law of large number because it follows the convergence in probability. Okay, this law is called the weak law of, suppose this condition satisfied, then if this condition satisfied, then we claim that we conclude that the sequence of random variable obeys weak law of large number. And this is called weak law of large number because it follows the convergence in probability. And we have discussed in the above, the convergence in probability is weak in nature. It is a weak convergence, so that's why it is called weak law of large number. In a same manner, strong law of large number is there. Okay, and in that, those sequence of random variables actually follows the convergence almost surely. So since it is a stronger one, or we can say that one of the strongest modes of convergence, so that's why that law is called as strong law of large number, that we will discuss after 10 minutes something. Okay, so this. Now there is one more, the Bernoulli law of large number is there as an example. Let me write. Okay, so let me write it in a theorem form actually. Like Bernoulli's law of large number. Okay, so again, let x1, x2, xn be a sequence of IID random variables. Okay, having a Bernoulli distribution with parameter p. Then for any epsilon greater than 0, we have probability that x1 plus x2 plus xn divided by n minus mean. Here the for the Bernoulli distribution, the mean is p itself. So minus p greater than 0, sorry, greater than epsilon is nothing but 1 upon 4 times n epsilon square. Okay, so this is the law of Bernoulli's law of large number. Okay, so let's discuss one example based on the law of large number. We have discussed till the, like, suppose we have performed an experiment, a random experiment of rolling a die. Okay, and the favorable event is defined as like getting number 5. Okay, so now for a given epsilon, now take or consider epsilon, the value of epsilon is 0.01. Then our question is, what is the minimum number of Bernoullian trials? What is the minimum number of Bernoulli trials such that probability that this x bar minus p is less than epsilon is greater than 95% of the time, that is 0.95. Okay, so this is the question. We need to find the minimum number of trials, that means the value of n for which this getting a 5 after rolling a die, getting a 5 at epsilon equal to 0.01 has the probability 95% when we have considered the stretch is x bar minus p is less than 0.01. Okay, so let's start. Here, like, since probability of A is what? Getting a 5. Since it is a die, it is a fair die. So probability of getting a 5 once we roll a die is nothing but 1 by 6. Okay. Also, epsilon is already given here, 0.01. So the probability that the x bar minus 1 by 6 is less than 0.01 is greater than 0.95. We need to find the value of n here. Here, since x bar is nothing but x1 plus x2 plus xn whole divided by n. So this implies probability that x bar minus p less than epsilon is greater than 1 minus p 1 minus p and divided by n sigma square. This is p1 minus p is nothing but the variance when it follows the Bernoulli distribution. For Bernoulli distribution, the mean is p and the variance is p1 minus p. So here we have written in the same format. Okay. So now since we have this, okay, and now this is the from the definition only. Okay. So just compare these two. Okay, so left hand sides are equal, right hand sides we need to compare. And once we are able to simplify this, we will find out n is greater than p1 minus p whole divided by 0.05 and 0.01 whole square. And after solving, we will get the approximate value of 27,778. So that means we need to roll 27,778 times a fair die so that we get number 5 up 95% of the number 5 up to this stretch. The stretch is like the average value, the sample mean minus the probability of success, and the range will be like 0.01. Okay. So this is how we calculate. Now the next is we will discuss about the strong law of large number. Okay. Is it okay up to this point? Na?
Yes, sir.
Am I audible? Na?
Yes, sir.
So now this is strong law of large number, SLLN. Okay. Again, the similarly we can define like let x1, x2, xn be a sequence of IID random variable. Here IID random variables is there with finite mean, suppose mu, and finite variance, sigma square. Okay. Then like x1 hello, hello.
Hello. Hello.
Is my screen visible?
Yes, sir.
Okay, okay. Actually, there is a network issue. Now my screen and as visible, na? Strong law of large number is there.
Yes, sir.
Okay, thank you, thank you. Okay, so now here strong law of large numbers like let x1, x2, xn be a sequence of random IID random variables with finite mean mu and finite variance sigma square. Then like x1 plus x2 plus xn divided by n, which is the sample mean, is almost surely converges to mu, or we can say that x bar is almost surely converges to the population mean mu, or we can write it like the probability that limit n tends to infinity, x bar is nothing but mu, and the probability of this is nothing but 1. Okay, so this is the strong law of large number. Okay, now the last topic that we will discuss today is central limit theorem, which is abbreviately called as CLT. Okay, so there are the various forms of central limit theorem. We will discuss one of the simplest one. Okay, so the simplest one, let me write the definition. Let omega f p be a probability space. Okay, also let x1 x2 dot be a sequence of IID random variables. Okay, defined on the probability space omega f and p. Now assume that expected value of xi equal to mu and variance of xi equal to sigma square, which is greater than 0, obviously, for all I equal to 1, 2, and so on exist. So that means at least second order moment should exist. Okay, and that will be finite. So now defining a new sequence of random variable. Okay, now defining a new sequence of random variables, and that is defined like z. Zn equal to summation of xi I from 1 to n minus expectation of summation of xi I from 1 to n. This divided by the under root of variance of summation of xi I from 1 to n. Okay, this random variable, okay, this for n equal to, obviously, this random variable, okay, this new random variable or the sequence of random variable actually, then for large n, this new random variable or the sequence of random variable zn is approximately standard just a second, approximately standard normally distributed random variable. So that means we can like say that probability that zn less than a value z is approximately nothing but 1 upon root 2 pi e to the power minus t square by 2 dt. So this is nothing but the PDF of the standard normal distribution. Okay, so here we see that the new sequence of random variable follows the standard normal distribution, and here we have defined in the expression zn equal to summation xi minus expectation of summation xi divided by under root of variance of summation xi In this expression, we like take deviation from the xi, summation xi, with their expected value of summation xi. That is actually called the standardization of the random variables. Okay. And in short, we claim that, or we say that the summation xi should also approximately follow the normal distribution. That doesn't mean like x1 follows some distribution, x2 follows some other distribution, x3 follows some other distribution with different parameter values. But once we take the summation of all those random variables, then that is approximately normally distributed. Okay. And in a similar manner, once summation xi is approximately normally distributed, then the standardization of this random variable should also follow the standard normally distributed. Okay. And this is the central limit theorem. Okay. There are various versions of central limit theorem. Some advanced version is also there, but this is the simplest one and like quite convincing one, that how the central limit theorem works. Also, there is one more point. Here we have considered the IID random variables. Like we have a probability space omega fp. Okay. And also we have considered the sequence of random variables are IID random variables actually. But if we will not consider the identical word, okay, independent will be there. But if it is only independent but not identical, then in that case, expectation of xi equal to mu I and variance of xi equal to sigma I square is there. Okay. And again, this theorem follows the same result and will lead to the will lead to the a new random sequence of random variables, which again approximately distributed as standard normal variable. Okay. So if we like omit the identical word from the definition, then again this distribution follow the same. But if it is independent, then it may possible or may not depend on the condition. Okay. So this is the central limit theorem. So these are the topics we have discussed in the 8th week of the course. So if there is any doubt, any questions, you people may ask. If not, then let's start solving some numericals. Is it?
Okay, sir.
Okay, then let's start some numericals. Sorry. So there is a question like let xi I from 1 to be a sequence of IID random variables with common PDF probability that xi equal to 1 is p and probability that xi equal to 0 is 1 minus p for the p lies within 0 to 1. Now let's define a random variable, a new random variable x, which is summation of xi for I equal to 1 to 10. This new random variable is defined. Now, for p equal to 1 by 2, find probability that x less than or equal to 4. Exactly. That means since we are given, it is nothing but the PDF is nothing but the Bernoulli distribution actually. Okay, so we know the distribution. So we can calculate the probability that x is less than or equal to 4 exactly with the help of the Bernoulli distribution. Also, calculate the probability that x is less than or equal to 4, like using central limit theorem. Okay. Now using the approximate way, that is us using central limit theorem, we need to calculate the probability that x is less than or equal to 4 and then compare the results. Okay. So let's start. Now for the first case, here x follows actually Bernoulli, if you can see. Okay. And sorry, xi. Okay. And x, which is defined as the summation of xi, is nothing but summation of 10 Bernoullian trials. Okay. So that means x follows binomial distribution with parameter n equal to 10 and p equal to, we are given p equal to half. Okay. So np is there, n equal to 10, p equal to half. So the probability that x is less than or equal to 4 is nothing but, like we can write now, probability that x equal to 0 plus probability x equal to 1 plus probability x equal to 2 plus probability x equal to 3 plus probability x equal to 4. Okay, so we can solve this like we can write like this as well. I from 0 to 4 nci p to the power I and 1 minus p to the power n minus I. Okay, so using this, putting the values of n equal to 10, p equal to half, and I equal to 0, 1, 2, 3, and 4, we are able to calculate the exact probability for the problems. And once we are able to solve, we will find the probability 0.3770. Okay, so this is the exact probability that x lies less than or equal to 4. Okay, now using the central limit theorem. Okay, the same question. Like now, since for central limit theorem, we need the expected value and the variance. Okay, but we don't need the distribution. So for the expectation of x, since we are given the probability of success is half and the total number of trials will be 10. So the expected value of x is 10 into half, that is equal to 5. And the variance of x is, again, since it is Bernoulli kind of, variance of summation of xi is there. And the variance of xi is nothing but pq. So 10 into pq is there. So 10 into half into half. Q is nothing but 1 minus p actually. So it is 5 by 2. So we have the expected value and the variance of the random variable. So now, sorry, now using the CLT, the probability that x lie less than or equal to 4 is equal to probability that just standardize this random variable x minus expectation of x. Expectation of x is 5 divided by positive square root of variance of x, that is under root of 5 by 2. Less than or equal to 4 minus 5 divided by under root of 5 by 2. Okay, simple. And we know that it is approximately normally distributed, standard normal distribution. So that means it is z, and less than or equal to 4 minus 5, that is minus 1 divided by under root of 5 by 2. Once you will solve, you will find minus 0.36. Okay, so now again, okay, this is actually approximately normally distributed now. So once like you are able to like think, then you will find, suppose this is the value minus 0.63. Okay, so we need to find the probability that z is less than or equal to this. So that means we need to find this area only. Okay. So obviously, if you use the normal table, you will find the probability that x is less than or equal to this. Using the normal table, you will find definitely it is phi of minus 0.63, which is nothing but 0.2663. Okay, so using the approximation method, we will find the probability that x is less than or equal to 4 is 0.2663. Okay, so this is how we use central limit theorem. Okay, here like we are able to calculate the probability for the exact with the help of the exact distribution and using the central limit theorem both. But there are some cases when we are not able to calculate the probability or other statistical characteristics with the help of the direct distribution only. Okay, so we use central limit theorem there only. Like we have an example. Okay, like suppose a fair die is rolled 1000 times. Okay, find the probability that the number 4 appears at least 150 times. Okay, so now, hello, is there any question?
No, sir.
Okay, okay. So now the question is कि हमें like we need to find the probability that 4 appears at least 150 times when we roll a die, a fair die 1000 times. Okay, so this is the question. Now we know that here we know that x follows binomial. Okay, but let's give like here the random variable x is nothing but getting a 4. Okay, and now we need to find the probability that x is greater than or equal to 150. Na? This is the probability we are going to evaluate. Na? Find the probability that the number 4 appears at least 150 times. So either at least 150 or more than that. Okay. So obviously here x follows a binomial with parameter 1000. And since we are rolling a die, the probability of getting a 4 is nothing but 1 by 6. Okay. So this is how. So the probability of x is greater than or equal to 150 is defined as like this, na? Summation I from 150 to 1000, 1000 ci 1 by 6 to the power I, 5 by 6 to the power 1000 minus I. Okay, so this is the actual probability actually. Okay, this is the exact probability for the question. But as we can see, we are not able to evaluate this probability. Okay, so how can we solve? So we use some approximation method or some other statistical concepts to calculate this probability. Okay, so like here we see that since like it is quite tedious. It is quite tedious to calculate the probability. So we use central limit theorem. Okay. So we are not able to calculate the exact probability. So we use central limit theorem. And once we are going to use the central limit theorem, we need expected value and the variability or the variance. Okay. So the next step is to calculate the expected value. Now the expectation of x, simply since we have performed 1000 times, the rolling a die 1000 times, and the probability of getting 4 is 1 by 6. So it is approximately like 1000 by 6 or like 500 by 3 is there. Okay, so this is the expected value. Similarly, the variance of x is NPQ for the binomial. So it is 1000 into 1 by 6 into 5 by 6. So this is defined as like, okay, 5000 by 36, or you may simplify, or we will simplify it further. Okay, now using CLT, we need to find the probability that x is greater than or equal to 150. This is like x minus expected value of x, that is 500 by 3, divided by, actually this value is approximately 25 root 2 divided by 3. Okay, so okay, so x minus expected value of x divided by, this is a square actually. Okay, divided by 25 root 2 divided by 3. Okay, is greater than or equal to 150 minus 500 by 3 divided by 25 root 2 divided by 3. Okay, so as we know that for central limit theorem, the first part, the x minus expectation of x divided by standard deviation of x, is approximately normally distributed. So we have considered is z greater than 150 minus 500 divided by 3 divided by 25 root 2 divided by 3. This quantity is simplifying by, sorry, 1.414. So z is greater than minus or equal to can also be there, but since it is a like a continuous distribution, then doesn't mean we put the sign equal to or not. So z is greater than or equal to minus times of 1.414. Okay, so if like you wish to draw the curve, okay, so this is the curve, suppose. So for example, this is minus 1.414. So the probability that z is greater than or equal to minus 1.414 is this. Okay, so obviously it is quite more than 50%. Okay, so it is like 1 minus phi of minus 1.414. When you use the normal table, you will find out 0.7865. So probability that x is greater than or equal to 150 is nothing but 0.9213. So this is the probability using the help of central limit theorem. Okay, so this is how the central limit theorem is used. Okay, now there are some more questions. Okay, now we have a question like, let x1, x2, x3 be a sequence of random variables such that xn follows binomial distribution with parameter n and lambda by n. Okay, for n belongs to the natural number n and n is greater than lambda as well, so that n by lambda is always less than 1. Okay, where like lambda is also greater than 0, it is always greater than 0, is a constant as well. Now we need to find, or we need to show that this sequence of random variable xn converges to some other distribution or not. If, then which distribution it is. Okay. Okay. So like find the convergence of the xn. Okay. So let's start, okay, with the distribution. Because we are given the distribution, we have a known distribution, so we can proceed in the similar manner that which distribution it is going to follow. Okay, so the solution will be like the first, since for the like for the convergence in distribution, we need to like n tends to infinity, okay, xn of k. For example, f k, you can write anything, x of k for all k equal to 0, 1, and so on. Okay, so this is the distribution is, sorry, convergence in distribution. This is the definition for the convergence in distribution. So here, take the left hand limit, limit n tends to infinity. The given probability function is xn k, which is equal to like, consider limit n tends to infinity. Here pxn is given n, xn follows binomial n or lambda by n. So since we are given the parameter, so we can like use the PMF form, NCK P. P here P is equal to like lambda by n. Lambda by n to the power k and 1 minus lambda by n to the power n minus k. Simple. Since lambda k is independent of n, so we can write like this. Lambda k is taken outside from the limit. Limit n tends to k. NCK is nothing but n factorial, k factorial, and n minus k factorial. Okay, and okay, and since lambda k is taken outside, so this quantity is like 1 by n to the power k, and the next one is 1 minus lambda by n to the power n minus k. Simple. Now, in denominator, in the under the limit in denominator, k factorial is there, so it is lambda k to the divided by k factorial is there. Now limit n tends to infinity. So if you can see, you will find n factorial divided by n minus k factorial. Actually, this can be written as n minus 1 up to n minus k plus 1 factorial divided by nk. N to the power k is nothing but the 1 by n to whole power k is there. So we have like written in together, and 1 minus lambda by n to the power k can be written as 1 minus lambda by n to the power n is there, and also 1 minus lambda by n to the power minus k is there. Okay, so we can write like this. If you may notice, we can write like this actually. Okay, so the above expression can be written in this format. Now, for a fixed k here, we have three different actually like terms in the last expression. So for a different or for a fixed k, like for a fixed k, this value like limit n tends to infinity, like n minus 1, n minus k plus 1, and divided by n to the power k. This limit, after solving, we will get this limit value is 1. Okay. Also, the second term, like limit n tends to infinity, 1 minus lambda by n to the power minus k. Since n tends to infinity, so lambda by n tends to 0. Okay, this implies this is nothing but 1. Okay, is it clear? And the next one is like limit n tends to infinity 1 minus lambda by n to the power n. This is nothing but the expression for the e to the power minus lambda. Okay, this is well known. So e to the power minus lambda, 1 and 1 is there. So putting these value in this expression, in the final expression, we conclude limit n tends to infinity xn k is e to the power minus lambda, lambda to the power x upon, sorry, not x, it's k actually, k upon k factorial. Okay, this is nothing but the probability mass function for the Poisson distribution. So this implies x follows Poisson distribution with parameter lambda. So this means what? This means we can say that thus we conclude that like xn converges to Poisson lambda in in distribution. We are taking the concept of distribution. So in distribution. So this is the answer. So we say that the sequence of random variable xn converges to Poisson distribution with the parameter lambda in distribution. The convergence in distribution takes place. I hope this is like clear. If you have doubt, then please ask. Okay. If not, then let's move for the next question. Is it okay? Let Am I audible? Na?
Yes, sir.
Okay. Let xn follows. Let xn follows exponential. Sorry. Exponential lambda distribution. Then we need to find the xn converges to probability at which point. Okay. We need to find the convergence in probability. Then find the like convergence in probability. Okay, for the xn. Here like since xn follows exponential lambda, so that means fxn of x is nothing but lambda e to the power minus lambda x, for lambda is greater than 0, x is greater than 0. Okay. Now for the convergence in probability, like for convergence in probability, we will write like xn converges to x in probability if for any epsilon greater than 0, this limit n tends to infinity probability that absolute of xn minus x is greater than epsilon, this probability must equals 0. Okay, so let's start taking the RHS or taking the condition. Limit n tends to infinity. Okay, probability that xn minus x. Let's consider the value of x is 0 here. Okay, because there are actually options here. Okay, so we can write 0 as well, 1 as well. So when we write 0 and is greater than or equal to epsilon, it is defined as limit n tends to infinity, probability that xn is greater than or equal to epsilon. Okay. If you see that, you will find that probability that xn is greater than or equal to epsilon is nothing but 1 minus probability that xn is less than or equal to epsilon. Okay. You may like omit the value epsilon actually here. Okay. So here this is nothing but the survival or 1 minus CDF. This is the definition for the 1 minus CDF, which is probability that xn is greater than epsilon. So this means what? This means limit n tends to infinity. The value of this is e to the power minus n epsilon. Okay. Since xn is positive and xn follows like exponential n. Okay. Like here, if you can write the CDF is also like 1 minus e to the power minus lambda x. So the probability that x is greater than x is nothing but e to the power minus lambda x. So in a similar manner, we can write here like this, e to the power minus lambda epsilon. And this value, obviously nothing but 0 for all epsilon greater than 0. So limit n tends to infinity, the probability value is 0. So this implies xn follows, converges to 0 in probability. So here xn converges to 0 in probability. Hope this question useful to understand. Okay. If not, please ask. If yes, then let's go for some other question. Now the next question. This question is based on central limit theorem actually. A bank teller serves customers standing in the queue, customers standing in the queue one by one. Okay. Suppose that the service time, the question is, suppose that the service time xi, service time xi for customer I has mean expectation of xi is 2 minutes and variance of xi equal to 1 minute. Okay. Now we assume that we assume that the service times for different bank customers are independent. Customers are independent. Let y be the total time let I be the total time y be the total time the bank teller spends serving 50 customers. Then we need to find or we need to calculate then calculate probability that this total time lies between 90 to 100. Okay, that means we need to find the probability that y, that is the total time, lies within 90 minutes to 110 minutes. Okay, so again, uh, we will use central limit theorem to evaluate the probability. So let's start. Okay, just have a look once. A bank teller serves customer standing in the queue one by one. Suppose that the service time xi for customer I has mean expectation of xi is 2 and variance of xi is 1. Now assume that the service time for different bank customers are independent in nature, and then the another random variable y is defined, that is the total time the bank teller spent serving 50 customers. Now we need to find the probability that the value of y lies within the ranges 90 to 110. So let's start with the like here we are given xi is the service time. Okay, for the ith customer, and also uh, here y is defined as like x1 plus x2 plus xn. Okay, here n is taken as 50 in the question. Expectation of xi is taken as 2 minutes and variance of xi is considered as 1. Okay, so the probability that 90, this can be standardized like in this format, 90 minus, first we need to find the expected value of y actually. Okay, so let me write it later actually. Okay, so expected value of y is what? Expected value of x1 plus x2 plus xn. These are independently distributed, that is expectation of x1 plus expectation of x2 plus expectation of xn. So it is 2 actually, if you can see. Okay, so 50 into 2, that is 100 minutes. Okay, and now the next is variance of y. So the variance of y is variance of x1 plus x2 plus xn. We are given these are independent in nature, so that is variance of x1 plus variance of x2 plus variance of xn is there. And since n is square 50, so after calculation root, like we can write like 50 into 1, that is 50 here. Okay, 50 times is there and the variance is given 1. So now we will perform the central limit theorem. So probability that 90,110 is probability that 90 minus expected value of this, that is 100, divided by root 50, because variance is 50. So under root 50, this one is like y minus 100 divided by root 50. Again, it is 110 minus 100 divided by root 50. Okay, it is simple. As we know that it is minus 10 upon root 50 less than, we know that this y minus 100 upon under root 50 is nothing but approximately normal distributed, standard normal distribution. Okay, so this is 10 by root 50. So simply it's simplifying like this, root 2 minus times z plus root 2. Okay, so the value of root 2 is approximately 1.4 something, 1 point something. So if now we are going to use the normal table. Okay, so this is like phi of root 2 minus phi of minus of root 2. Okay, so that means if we are like draw the table something or the normal curve. Okay, so for example, this is root 2 and this is minus root 2. So we need to find the probability of this shaded portion or enclosed portion. So obviously this is since more than 1, so it is more than 50% undoubtedly. So once we use the normal table, we will find the probability that y lies between 90 to 110 is 0.8427. Okay, so just use your like table, normal table, you will find the values. Okay, we have already discussed how to use the normal table in the previous lectures. Okay, so this is how we solve the numericals based on this. Okay, so now we have one more questions. The question is, let y2, y3, y4 and so on be a sequence of random variables. Random variable such that fn f of yn, I mean f of yn of y is defined as like this: 1 minus 1 minus 1 by n to the power ny when y is greater than 0 and 0 otherwise. Okay. Now we need to again find the convergence in distribution. Okay. We need to find the convergence in distribution. We have actually 4 options here. So let me write like yn convergence in distribution to exponential 1 yn. The second option is convergence in distribution to exponential 2. The third one is yn converges in distribution to exponential 1 by 2. And the fourth one is yn converges in distribution to exponential 1 by 3. So we need to find which of the 4 option is correct. So let's start solving the numericals. Now for y is, since we are dealing with the exponential distribution, so for y is less than or equal to 0, we have f of yn of y is 0, which is equal to f of y, for example, for n equal to 0, 1, 2, and so on, not for n equal to 2 here actually, 2, 3, 4, and so on. Now, for y is greater than 0, we have like limit n tends to infinity f of yn of y. This is nothing but limit n tends to infinity. Yn is defined as 1 minus 1 by n to the power ny. Okay, so it is 1 minus 1 minus 1 by n to the power ny. Okay. So like 1 minus limit is going inside and tends to infinity. 1 minus 1 by n to the power ny. Okay. Now again, limit n tends to infinity. This particular quantity is actually e to the power lambda, or sorry, e to the power y actually, in terms of y, it is there. So it is 1 minus e to the power y. So for all y, so it is nothing but the CDF for the exponential one distribution, which is CDF for the exponential one. So that means this implies y follows exponential one. So that means we can say that yn converges to exponential one in distribution. Simple. Okay. We already know the distributional form of the functional form of the exponential distribution, and that's why we are able to recognize which distribution y follows. Okay. So this is the case. Now we have one more question. Sorry. There's one more question. The question will be like, let yn follows uniform 0 1 by n. Okay. Then which of the following is correct? Which of the following is correct? Like the first option will be like yn converges to 1 by 2, or any r is greater than or equal to 1. B will be like yn converges to y for any r is greater than or equal to 1. The C1 is yn converges to 1 for any r is greater than or equal to 1. And the D1 is yn converges to 0 for any r is less than or equal to 1. Sorry, r is greater than or equal to 1, not less than or equal to. So that means we are going to discuss about the moments. Okay, convergence in moment. So if you may recall, we have already discussed in the previous slides. Okay, so if you may recall, you may find the expectation of x, absolute of xr should be unique, so should be finite, and limit n tends to infinity, expected value of xn minus x to the power r must be equal to 0. This is the case, or this is the definition for the convergence in moment. Okay. So just using the same logic or same concept, we are given, we will solve the numericals. This is the just for remember. Okay, so the PDF of yn is what? Here the yn follows uniform 0 1 by n. Uniform 0 1 by n. So that means the PDF of yn is nothing but n when y follows this, otherwise 0. Okay, so this is, now we will calculate the expected value. So now we have expectation of yn, suppose minus 0 is there. So it is nothing but 0 to 1 by n, y to the power r into the PD of n is there, dy. Okay, so this is nothing but n y to the power r plus 1 upon r plus 1, 0 to 1 by n. Okay, so just putting the values and nothing else. So it is putting 1 by n. So that means 1 upon r plus 1 or n to the power r. And now as n tends to infinity, since it is in denominator, this value converges to 0. So that means this expected value converges to 0 for all r is greater than or equal to 1. So that means our uh, option D, option D is the correct one. Okay, so that means thus we can say that like yn converges to 0 for any r is greater than or equal to 1. Okay, so this is how we solve. Now there is one more question. Okay, so there are 100 men on a plane. Is it visible? Is it, am I audible? Anyone? There are 100 men
Yes, sir.
on a plane. There are 100 men on a plane. Let xi be the weight. Let xi be the weight in pounds of the ith man on the plane. Okay, suppose that the xi's are IIDs and expectation of xi, which is equal to mu, is equal to 170, and sigma of xi, which is sigma equal to 30. Now then the probability that that the total weight of the men, the total weight of the men on the plane exceeds 18,000 pounds. Okay, so this is the question. We need to find the probability that the total weight of the men on the plane exceeds 80,000 pounds. Okay, again, similar question. We use central limit theorem. Okay, so here like xi is defined as like weight of the ith man. weight of the ith man. Okay, and we define W, for example, which is equal to x1 plus x2 plus xn, that is total weight, total weight of n men. Okay, now here n equal to actually 100 is given. So the expected value of x actually given. Expected value of x is given 170 and and sigma x is also given 30. So now we will calculate expected value of w actually. So expected nothing but summation is nothing but expected value of like x1 plus x2 plus xn. Since it is n times, so it is n times of mu, okay, which is equal to n times of 170. So expected value of W is 17,000. If you can write, it is in pound. Okay. So now the variance. Now the variance of W. Variance of W is 100 times of variance of X size. Again, similar logic because it is given IID. If you remember, these are like given IID here. Okay. So 100 times of variance of X. Now 100 times into variance of X is nothing but 30 square. So it is 90,000. Okay, 90,000. The variance of W is 90,000 with the expected value of W is 70,000 pound. Okay, now since it is sigma W is square, so sigma W is nothing but under root of 90,000, which is nothing but 300 actually. Okay, so now we need to calculate the probability that total weight on the plane of main obviously is greater than 80,000 pound. That means probability that W minus expected value, that is 70,000 pound, divided by the sigma W, which is 300, is greater than 80,000 minus 70,000 divided by 300. Clear? Simple. So it is nothing but approximately normally distributed. So let me write it said here, which is greater than 80,000 minus 1,000 divided by 300 actually. If you may notice, it is probability that Z is greater than 10 by 3. That means probability that Z is greater than 3.33 and so on actually. Okay, now uh, now if you people remember, we have discussed like for a normal curve, the 99.73% of the 99.73% of the area lie under the 3 sigma limit. Okay, so that means it is 1 2 3 1 2 3, for example. So this area contains 99.73%. Okay, this area contain mu plus minus 3 sigma. This area contain 99.73% of the probability. So we need to find the probability that Z live is greater than this. So maybe somewhere here it is 3.33 and the probability is greater. So this is the area. Okay, so this area is like 99.73 of the areas lie within 3 sigma limit, and that is very less. Okay, so if you may use some internet and other tool, you will find the exact area with the help of the table X, obviously. So this is nothing but just wait. This is nothing but 1 minus phi of 3.33, and that is 0. Not 0.43, sorry. This is 4.3. The approximate value is there actually, because we are not able to exactly calculate this value, 10 to the power minus 4. Okay, so the probability that the total weight of the men on the plane is greater than 18,000 pounds is approximately 4.3 into 10 to the power minus 4, which is quite less. Okay, so this is how we calculate the probability using the central limit theorem. So is there any doubt, any questions?
No, sir.
No. So if there is no question, I think we can conclude our session here. Okay. So if you people have any question, you may ask in the comment section of the YouTube channel, or via directly contact to me, or you can ask in the group or forum as well. Okay. So let me stop the recording.